All right, I think I'll go ahead and get started. So welcome everybody today for the Data Science Institute Data for Good seminar series. This week we are fortunate to have Dr. Ghassemi from the University of Toronto join us today to talk about explainable AI. Dr. Ghassemi, as I said, is an assistant professor at the University of Toronto in computer science and medicine. She's also a Vector Institute faculty member holding a Canadian CFAR AI chair. I'm not sure if I'm saying all of this exactly correctly.
That's all right, yeah, correct.
And a Canadian research chair. She's going to be moving to MIT in July 2021. She's done a whole host of really impressive things over the last few years. I do want to highlight, though, that her work has been featured in addition to widely sort of across academic outlets. She's been featured in popular press like MIT News, Huffington Post, and she has been named one of MIT Tech Review's 35 Innovators Under 35. So it's a real pleasure to have you here today, and we're looking forward to hearing about your work exploring models and machine learning for health. Thank you.
Thank you. So today, I'm going to talk a little bit about research that I'm doing and research that is sort of upcoming. But honestly, today you're also getting sort of a mildly evangelical talk about a topic that I think is really important in my research area, but is important in many research areas. And I want to give you this talk about explainability and why you think you don't explain yourself in AI and medicine, specifically because it's a really hot topic. It's something I feel really strongly about. And I think it's also the analogy that I use is that you could say that the patient is bleeding, right? And explainability is not the Band-Aid that you need for this hemorrhage. So my work generally works on exploring healthy models in machine learning for health. The reason that I think this is a really interesting time to be working in this space is that machine learning is already in the wild. So decades ago, people in intensive care units created these risk scores to try to stratify patients' severity of illness. And those are still used today. And, increasingly we've had alarms, alerts, risk scores, calibrations that clinicians use to try to assess patients for whether they need specific treatments, whether they should be early diagnosed for specific conditions. The reason that the conversation has changed recently, and it feels like maybe more people are talking about, oh, the AI is coming to medicine, is not because it hasn't been there, right? It's because now we have state-of-the-art methods that perform at or above human doctors across the range of the human lifespan. So this is really what changed the conversation. It's not just, well, I have a calculator, put the data in there, let me see the output. The conversation is now, but the calculator can do everything I can do in some cases better than I can for very tedious tasks or tasks that involve a lot of mechanical calibrations. But, my work focuses on creating actionable insights in human health. We focus really broadly on 3 different kinds of research. So first, trying to develop models and representations that work well for heterogeneous health data. And I call that what models are healthy. Second, trying to understand how to make models that work well in healthcare data robust, private, and fair so that they could potentially be deployed. That's what healthcare is healthy. And then finally, even if your model is very accurate, you have the right representations, even if it is robust, private, and fair, you have no idea how a human is going to use them. And so that's trying to figure out what behaviors are healthy once we contextualize the performance of a model with human interaction. A lot of what I'm going to talk about today is in that last bucket. So you might ask the question, we're talking about explainability and maybe transparency is the big umbrella term for that. Why do you even want transparency in model? Who started this ship? Well, I think that the reason it's become a big topic in medicine specifically is because there's a huge interdisciplinary mismatch and expectation that comes from a difference in expertise. And so you have maybe a clinician who says, I have this really hard problem, And then a machine learning person comes in and says, well, I have the algorithms, right? So we're good, right? And then 6 months later or a PhD later, the problem is not solved. And so I think that this has caused a sort of demand for, well, you think you're fixing a problem, our problem is not fixed. Why can't you just be more transparent about what's going on? And maybe that will help with this mismatch. I think this is the wrong Band-Aid. And so for this talk, I'm going to talk about explainability as sort of one way of interpreting what transparency could mean, because it's a very common way of interpreting, the desire for transparency, but there are other definitions one could use. So the first thing I would like to state, and this is based on social science research, is you can get people to trust explanations, and specifically in the robotics community, this is work by Ayanna Howard at Georgia Tech, you can get humans to over-trust robots. And robots seem to get over-trusted by humans in two different scenarios, where the person believes that the robot can perform a function they cannot. This happens in medicine all the time. I can't take an MRI. I can't, make the lab test numbers come out. So, check that box. Or when the expectation is that the system will mitigate risks. Again, this happens in medicine all the time, where I imagine that if there's a contraindication for 2 drugs, the system will tell me, right? If I've overdosed something and, the blood pressure goes out of range, the system will tell me. So that box is also checked. So just keep in the back of your mind that purely from other areas of research about human trust in explanations, the deck is loaded, all right? We're probably going to overtrust things we see anyway. And then the thing that sort of kicked off my recent worries is that I have a good friend, Sanmi Kuyejo, who was at UIUC. He was doing this experiment where he needed to generate, as step 1 of his evaluation, these chest x-rays, right? And so you train a generative model, it sees lots of examples of chest x-rays, and then it's supposed to make a new one, right? An unseen one, right? And step 1, to show that you're doing that well enough, is showing that the experts, in this case doctors, can't tell the difference between the real chest x-rays and the ones that you generated, right? That makes sense. It's a Turing test, sort of a variation, right? And so what he expected is, he would just have this, 50%. Doctors are no better than chance. Or maybe my images are not that good. And so, maybe just below the chance. So doctors can tell like 60% of the time that it's a fake chest x-ray. That is not what he found. He found that individual doctors have incredibly strong personal preferences about whether they think GAN images, the fake images, are real, or the real images, the actual chest x-ray images, are real. I mean, what he wanted to see was a bunch of dots around this line right here in the middle, right? Saying like, oh, we're generating images that are so good that they can't tell the difference any better than chance. Or he expected something sort of below the line where people favor the real images. But again, that is not what he's seeing here. There's this really broad range of individual responses. And this led us to wonder, in the chest x-ray setting, health is really about human decision-making, right? Humans make choices. And if our goal is ultimately to have improved care, we need to think about how advice is going to be received by expert and non-expert clinical decision makers. So in the case of chest x-rays specifically, an expert would be a radiologist because they see them all the time. And then a non-expert would be an emergency or internal medicine clinician because they see x-rays a lot, but it's not their sole thing that they do. So experts and non-experts. We wanted to examine what role accuracy plays. So do you trust accurate advice more? And then also, is advice rated differently if you think it's from an AI? So we set up an experiment where we recruited a bunch of doctors, so 138 doctors from 2 different categories, radiologists and also IMEM doctors. And then we gave them real chest x-rays where we had real patient information, and we changed 2 things. Number 1, we changed whether we said the source of the advice was AI or a human expert. In all cases, it was us. There's no model here, okay? We just said that it was from an AI or it was from a human doctor. And then we changed whether we gave them accurate or inaccurate advice. Okay, so there's two things we varied: the accuracy of the advice and then whether we said the advice came from. Okay, and then we measured whether the doctors got the final diagnosis correct and how they rated the advice itself. We found some unexpected things. The first is that task experts, so radiologists, rate AI advice significantly lower than human advice, even though it's the same advice. So they rate it statistically significantly lower in a way that IMEM doctors do not. Second, even though they rate it much lower, same advice, they rate it much lower. It's very low quality in their mind. They are just as accurate. They're a little bit more accurate using AI advice. So both IMEM clinicians and radiologists, and again, it's the same advice. I cannot stress this more strongly. This is very unexpected. So as you expect, radiologists are more accurate because they're experts. IMEM doctors are pretty good too. But you're a little bit more, not statistically significantly, but a little bit more accurate using AI advice, but just that their perception of the quality is very different. Perhaps more surprisingly, so we expected, at least the experts, we expected the expert radiologists to be able to dismiss the incorrect advice, right? So, sometimes we give them inaccurate advice, but we found that the anchoring effect was so strong that even though experts generally have a better diagnostic accuracy, right? So here's the diagnostic accuracy for radiologists. Here's the diagnostic accuracy for IMEM doctors. And if you pick an individual radiologist, like radiologist 60 here, you can see he got 25, 50, 60% of his cases right? But notice his line is completely blue because every single case that he saw and he got right, that we're counting here, he got right under accurate advice. There's no red bar, so he never got a case right when he was given inaccurate advice. These doctors over here, right? So this doctor right here got all of their cases right. The 2 incorrect advice cases that we gave him, and then every other advice case as well with correct advice. So you'll see there's very few non-expert doctors that got this correct, right? But really what we were most surprised by is how many doctors were susceptible to incorrect advice just in general, how strong this anchoring effect was, whether it was AI or human, right? Whether we said it was AI or said it was human. And this is not unique to this setting of chest x-rays and 2 different kinds of experts looking at diagnostic task. There's this great paper that came out this year in Nature Medicine about human-computer collaboration for skin cancer recognition. And the point of the paper is this blurb, this is straight out of their abstract, that there's good quality AI-based support for clinical decision-making. It improves diagnostic accuracy. But then buried in subfigure 2I is this little thing that I cut out and blew up because I think it's the most interesting thing in the entire paper. You will see that, yes, when they give the good AI predictions, because it's in sample, it's well calibrated, it's validated on this exact data set, there is benefit to interaction. You become more accurate, and especially more accurate for the more junior people, right? The effect is still positive, but goes down as you become more experienced. When you get the wrong AI prediction, the effect is very negative, and it's more negative than it is positive when the AI is correct. So I think this is, for me, the most interesting thing that I pulled out of this paper, because what it's saying is that when you have a model that is incorrect, whether the purported source is AI or human, the effect of that advice when it's incorrect is so much stronger and so much worse than the positive effect of that advice when it's correct. So this, the next thing that I want to convince you of is that explainability is not a panacea, right? So maybe you would say, well, the reason that people get tricked by this kind of advice is that there's no way for them to investigate it. And so it just looks sort of official and trustworthy, right? It's a number. But there's recent work by the group at Microsoft Research in New York that found that the interplay between machine learning and human decisions is not improved when you have more transparent models. So in this case, they tried to have people predict prices for the New York housing market. And they would say, here's the description of the unit, here's the rental price that our model recommends, do you agree with that? And they found that if you gave a black box model, people were able to catch silly mistakes the model had made, right? Where, for example, if you say it's a, 1 bedroom, 5 bathroom unit, it shouldn't go for the, you shouldn't just count up the rooms and say, well, there's 6 rooms, and so it should go for a really high price, right? Because it's 1 bedroom and 5 bathrooms. But when they used a clear model, meaning it was simple features, like it said, oh, number bedrooms times this minus this, so people thought they understood it, it hampered people's ability to detect when the model made those serious mistakes. And so in this case, this paper found that models that were more transparent made all the people that they surveyed in their experiment feel like their choice was good because the model agreed, right? And it's a transparent model. And so they didn't do this more aggressive audit of a mistake. And in medicine, you might be saying, oh, well, medicine's not like the New York housing market, right? Like, it's about evidence, it's justified in science, right? But medicine is subject to a lot of fluctuation and variation. So there's this great paper that showed in the past 10 years, around 400 papers were published that were medical reversals. And this is in JAMA, the New England Journal, the Lancet, really, really high impact clinical journals that are contradicting routine practices. So they're saying, oh, this thing that we do, that's bad, we shouldn't do it, that's harmful. So if you train a model to say that, oh, these routine practices are great, it's possible that they'll just become invalidated because we figure out, oh, that's not really what we should have been doing this whole time. We also don't audit doctors for accuracy or performance. There's no federal body that regulates doctors and makes sure that Dr. Ghassemi doesn't kill every Black woman she sees in her practice. In fact, on a state-by-state basis, where medical licenses are reviewed by a board and could be revoked, there's wide variation in the practices for which you might take away a license. And so there's no systemic audit that's done by any specific federal or state entity to ensure that you're meeting some minimum threshold of performance. Finally, it's been very well established that individual doctors can have really strong personal preferences about what patients they want to see. If you know a doctor personally, say this and they'll nod their head, yes. Or the treatments they like to give. Often treatment guidelines are a little open-ended. And so they'll say things like, choose a vasopressor and administer a proportional dose. There are a lot of different vasopressors that have a lot of different properties, and dosing requirements are often, again, loose guidelines that are not well established by patient gender, patient weight, patient genetic background. And so these are all factors that vary quite a bit. So now that I've sort of set you up to say, maybe explainability is the wrong Band-Aid for this hemorrhaging patient, I'm going to give you some arguments for explainable models, and then I'll destroy some of them. So the arguments are, number one, maybe it's just a principle or a regulatory standard. So like GDPR states that all people have the right to meaningful information about the logic of algorithms that defend them or that affect them. I have no argument against this one. This is actually just a really good argument. If it's a regulatory standard, then the federal or state body that regulates what these explanations should be should lay out clear guidelines for how explanations should be generated and what it means to be explainable or interpretable. That's fine, right? Another argument you might have is it's necessary in high-risk situations because these experts, like clinicians, they need explainable models, especially in high-risk areas. That's not true. What kind of experience what kind of transparency do we think we need for these experts? I'm telling you, doctors use black boxes all the time. We don't know how acetaminophen works. right? Nobody knows. You can Google this. How does acetaminophen work? No idea. People propose things every year and then it's invalidated. So we use black boxes in medicine constantly, things that we do not understand, but they seem to sort of work. It's important to have transparency when clinical opinion differs significantly from predictions. That's when it's really important. That doesn't mean that clinicians care about how the model works, as demonstrated by many, many, many tools in medicine. It also doesn't mean, as demonstrated by the New York housing market example, that you should build simple models for the sake of transparency. What it could mean is that you need to understand when to rely on or reject model outputs, that you need notification of what population the model might work on or fail on, or that you need to include limitations of the data that the model's trained on. There are some technical options for this that I want to walk through and then tell you why they don't work well. Number one, you could do transparency via post hoc explanations. So if you've read a computer vision paper in the past 5 years, this is what's really common, right? So post hoc explanations can be useful if they're consistent, which means the same model behavior gets the same explanation and different model behaviors get different explanations. I want to be very clear here that the common, popular, well-used attention-based explanations and saliency maps, the vanilla versions are not consistent. They do not guarantee consistency. There are fixes that have been proposed recently to try to make them more consistent, but they are not on their own consistent things for post hoc explanation. And so therefore, I think they're unsuitable if you're going to take anything to be even remotely close to a pragmatically deployable tool. There is also not consistency in other widely used tools like Lime or SHOP. Right? And so this is not just okay, I'm picking on like one tool for post hoc explanation because it's not, this is not a property of post hoc explanations. So many of the tools or techniques that are used for post hoc explainability are not robust. They don't help with things like attacks, and they are not consistent. They don't explain things in the same way. Here is a way that I have used post hoc explanations in my work that I found useful. So I wanted to predict interventions in intensive care units. And so we had 35,000 ICU patients, 5 static variables, 29 time varying labs and vitals, and then we had all of their clinical notes. So we processed all of these data into different matrices, concatenated them all so that we had one large matrix per patient of variables by time per hour. And then now that we have one matrix per patient, you can concatenate that across all the patients in the hospital and have a big tensor. That's great because there's a lot of ways that machine learning models can use tensors to model latent state or predict outcomes. I'm going to focus on a paper where we looked at recurrent and convolutional neural networks because these are often called more black box models, okay? What we did with post-hoc interpretability is we said the doctors were really frustrated that we used all of this data. They said, do you really need all of it? I mean, are you just using it to use it? And so we said, let's look at feature level occlusions. Let's remove specific data from the model and measure the post-hoc AUC hit. And so you see here that for something like invasive ventilation onset, the physiological data that varies hour to hour was most important. That's what really affected the AUC. But if we're talking about things like a fluid bolus in the intensive care unit, it's the note topics that we learned with a topic model that are most important. And so we went back to them and said, if you want to do many, many different intervention predictions at the same time, yes, actually we do need all of this data because all of it is informative for patient state, okay? The second thing that we did is we used convolutional filters. So we visualized the top 10 and bottom 10 most and least activating trajectories across important physiological variables that led to ventilation being predicted, for example, because they wanted to see, does this match with what we think we know a patient might have before they get a ventilator? And in the cases that I've outlined for ventilation, vasopressors, and non-invasive ventilation, they said, yeah, these signals make sense for what we might expect to see a neuron activate on if it's going to predict a need for something, okay? So what else might you use it for? So another thing that we used post-hoc explanations for is modeling the biological pathway continuum. So here there was an ask that we are able to take a specific latent variable of interest. So here it's increasing concentrations of a drug, and that we were able to visualize what a specific cell would do in response to that. And so there was this ask that the interpretability they wanted is they didn't want us to take all of the data that we had, combine it into one big representation, and then say, as some principal component variation moves, this is how the cell changes. They said, do whatever you want to the other data. We want this one specific thing held aside so that we can move that variable on its own and then see what your model would produce. Another technical option is transparency through natural outputs. So if transparency is just a way of calibrating clinical trust in a model, then maybe we could have clinicians and machine learning experts agree on metrics that are consumable in and of themselves, not an intermediate number that you need to explain, and delivering that end product on its own gives you the transparency you want. So the example for this is creating reports from clinical images. So what if instead of creating a risk score for specific diagnoses, we just wanted to automatically generate the radiology report that you would have written given a chest x-ray? This is not, I just want to stress, if you've done like image captioning where you have nice things that you need to write about an image, like, oh, there's a picture of a girl in a pink dress jumping in the air. So what I should caption this as is, girl in pink dress is jumping in air. In radiology reports, you have to predict the things that you might wanted to have said about the image and then explicitly confirm or deny that they're in the image, which for captioning would be something like, the girl in the pink dress is jumping in the air, there are no helicopters, and it's not snowing today. Like it's the equivalent of having to like first think about what you might want to confirm or deny, and then confirm or deny it. So here, what we ended up doing is saying, okay, we're going to first predict the topics that you might need to comment on in the report based on the image. And then we're going to conditionally generate sentences corresponding to the topic, right? So here you can see in the findings, there's no focal consolidation, effusion, or pneumothorax. In the impression, there's no pneumonia or pulmonary vascular congestion. So you have to know what you need to comment on. So the way that we did this is with a CNN, RNN, RNN architecture, which is not that complex, but actually worked really well for generating the scores we needed and the text that corresponds to it. The reason that this is important is it allows us to not just have a score like this, but to also deliver text as the end product. And so what this results in is having text that is readable, scores very high in readability, and also is clinically accurate. So it delivers on both of the things we actually want. And this beats other state-of-the-art models like show and tell or show, attend, and tell. The final thing that I want to cover in terms of a technical option is you could just have transparency by the audit of this embodied data, because health data comes from human bodies. And so in order to work with it, you might want to say that we need new tools to understand the process, not just the model. So we want tools like data sheets for data sets or model cards for model accuracy, because instead of just saying, oh, the model needs to explain itself, you should say, well, the process needs to be sort of understandable. I need to understand what data I started with, where it came from, and how that might influence the model outcome. The last thing that I want to say quickly, because I feel very strongly about issues of fairness, and I mean real fairness, not algorithmic fairness, is that there's an argument that black box models could create, increase, or propagate biases. Yes, that is true. But guess what? Those are already there. So there's lots of lovely epidemiological research that has demonstrated that doctors are humans, and humans are biased. So guess what? Doctors are also biased. So if there's a bias in society, it's going to be reflected in the care that's received. We've demonstrated previously that you see the variation in model performance that you might expect to see. So we are state-of-the-art models trained on ICU records, have varying performance levels based on patient gender, patient insurance type, and patient ethnicity. Even worse though, is maybe you've heard about, language models like GPT-2, GPT-3, BERT, right? These transformer models that can generate realistic text. You just feed them a sentence and they complete it for you, right? So we took a model called CyBERT that's trained on PubMed, the published medical articles that we can all read, not the trash of the internet. It's not trained on Reddit. And we gave it this sentence: race, patient became belligerent and violent, sent to. And if you start the sentence Caucasian, it fills in hospital. And if you start the sentence African American, Black, or African, it fills in prison. This is trained on PubMed. This is a language generation model that is trained with scientific articles, and this is what it created. This is not easy to audit. Like, how would you have found this bias if you didn't know to look for it? So the thing that I want to encourage people is, we want to improve care and practice. And I put this picture because the first time that I gave a talk about my work to a bunch of tech CEOs, they said, oh, we get what you're doing. You want to make a doctor like Dr. House. I said, no, he was a drug addict who abused his patients. I don't think we want to make a doctor like Dr. House, because doctors actually, this is pre-pandemic, report that they're very burned out. And burnt out doctors don't have time to be empathetic. But we know that empathetic care is a strong part of recovery and ultimately staying healthy. I think that some of the lessons that we should learn are, I did a brief project with the designers at Google Brain and a clinician at Verily in Cambridge, where we looked at what happened if you visualize data differently. What we wanted to do was ask clinicians to plan for healthcare interventions in a remote setting, and we showed them data in an ugly way and then in this pretty way. And what we found is that showing them data in this prettier way made them a lot more confident about their scores, but didn't make them more accurate. And so I'm also really worried that we're going to be in this regime where we'll show people information that makes them more confident, but not more accurate, because it's just easier to go with the advice, right? So instead of doing that, how might we improve care and practice? I want to point to an example that has bias. So it is well known, there's a study a couple years ago in the Proceedings of the National Academy of Sciences, that gender concordance increases a patient's probability of heart attack survivals, and that this effect is driven by male physicians treating female patients, which means if you come in with a heart attack, and there's all the other combinations: male doctor, female patient, male doctor, male patient, female doctor, male patient, female doctor, female patient, that male doctors have far more female patients die after a heart attack than any combination. There's this great quote from the paper: mortality rates decrease when male physicians practice with more female colleagues or have treated more female patients in the past. And the joke I always tell right now is that means that women are the best drug ever, because when you're around us more, you want to kill us less. But the actual serious thing that you should take from this is this part. When male physicians practice with more female colleagues, that's really meaningful, actually, because it means if somebody is around you telling you, you missed heart attack in that, go back. Like, if you are able to have somebody sort of say, the bias that you have is causing you to miss something important, refocus, then you can improve your practice and kill fewer female patients of heart attack. So I think that the future in this space is doing human and machine learning in the loop. We do need these new opportunities to improve collaboration between models and clinicians, because we know clinical care is not perfect now. And obviously we all want it to improve, but AI is not a panacea. It's going to have exactly the same problems that we do, and explainability doesn't fix that. So in summary, explanations and transparency are very important tools for debugging and auditing, but it's unclear to me how any expert or non-expert users can or should incorporate it. I think explanations have been demonstrated in a very wide range of settings to cause over-reliance and reduce our audit propensity. And biases that could be created, increased, or propagated should be tackled with aggressive audit standards that researchers and implementation teams are held to, not an explanation band-aid. This is work that's been done by a fantastic team of students and technical and clinical collaborators. And I hope I've convinced you that we can create actionable insights in human health. Thank you.
Wonderful. Thank you very much for Gosh, an informative, thought-provoking, all kinds of, it was just an excellent talk all the way around. Thank you very much. So just for folks who are in the attendee list, we do have a few minutes for questions. If you want to enter things in the Q&A now, we're going to take maybe 5 or 10 minutes to ask questions. One came up as you were speaking. Yanis Tsiligakis, sorry if I've mispronounced that, commented on the authority of advice as an important factor in whether or not people accept or reject that advice. Other important factors, though, have to do with somebody's livelihood or personal identity. That the example that he gives is that the ability to put food on the table might affect whether or not somebody is hesitant to accept a dissenting view regardless of its source. And I just sort of wanted to raise that and give you an opportunity to comment.
I think that's a really important thing to talk about. I think we have that problem now. So what I tell people about these really important ethical problems that come up is that these problems exist and we sweep them under the table with current clinical care, right? Because there's lots of really great literature that shows, for example, that Black patients are not given access to the same kind of maternal care. And that's why race concordance improves a Black baby's probability of survival and Black mom's probability of survival. And so authority of advice, a doctor telling you you don't need that treatment, or you're a resident, your attending telling you you don't need to give that treatment, is very important, because it's really hard to speak up against it unless you feel like you can, right? Or maybe you feel threatened. But there should be systems in place in all of these, honestly, life or death situations where you feel able to challenge advice. Those should be here now. And I think it's good that the idea that AI could come in and give advice is suddenly making people say, hey, well, how could I challenge that? What are those levers? Because I want those levers there now. It would be really great if there were ways for people who have a lot less authority to have sort of confidence and security that they can report on advice or treatments or recommendations that they think are being done really poorly. Because right now, if you know any doctors, you should talk to them about this, right? Like when I have 3 kids, and every time I would go to have a child, I would ask my friends, what do you think? And these are doctors who are practicing in some of the best academic medical centers in Boston, right? So these are fancy places. They would say, don't let Dr. X, preside over your delivery because he's past his prime, or Dr. Y seems to have a problem with any woman who's more educated than he is, so maybe don't talk to, they know these things. These are well-known things within the community. There are very few reporting structures that they can actually take advantage of. In fact, a lot of hospitals actually, because it's very difficult to say that somebody is killing all the Black women he sees, because then if you say, I fired this person because he's killing all the Black women he sees, every Black patient who's come through your practice is now going to sue you. So it's very common, if a doctor seems to be performing in a way that is not optimal, for you to let them retire and then move to another medical center. So I think that these structures should be in place, just because it's important, but I don't think that this is unique to AI.
Yeah, that's both interesting and terrifying. So thanks for that. So there are a couple of other questions that have come up in the window. One says, related to the quote, "What I cannot create, I do not understand. Should more clinical tasks be framed as text to text?"
I think it's hard to frame a lot of our clinical tasks as text to text. There are a lot of things that we don't understand from the human body, but it depends on the setting, right? So I think if you look at cardiology, for example, right? We understand ECGs pretty well, right? It's been well characterized that there are certain intervals that have certain meanings. But I think most of what we do with outpatient clinical care should be characterized as text to text. That's what they look at. If you actually look at what doctors spend time reviewing, they're reading through notes, right? And they're trying to elicit information from you. And so I think a lot of the non-critical care, non-acute care settings should be more text to text.
Great, thanks. One other question has come in. first, also Joyce is thanking you for a fantastic talk, and I want to be clear about that. And then ask the question, do you think the problem of over-relying on inaccurate advice would be ameliorated if doctors were better trained on what to do with the advice? For example, if they were better trained on understanding things given the accuracy rate of that advice?
No, I really don't. I think this is a human thing. I don't think that this is something that is easily addressed. I think we need to be very careful about the known strong anchoring effects of advice and about human over-reliance on advice.
Great. I'm going to ask, oh, there are actually a couple of more sort of coming in that I'd almost missed. Another devil that's hidden in the statistical aspect of AI models is in aggregation, which means we test on data that does not constitute a population. I believe we should only be using panel-style data, which follows more robustly the same individual over time. And the comment goes on, but I'll sort of stop there and maybe see if you can.
I think that that's a really important point, that a lot of what we do is measure aggregates, and that hides a lot of the tails of the distribution. Who do you think is in the tail of the distribution? Minorities, right? We have very strong theoretical guarantees that things like fairness and privacy and robustness work on the body of the distribution. But I mean, we're not a Gaussian. And even if we were, we're really stretched out Gaussian, and the tails are not places where you want to perform poorly.
Okay. One question, and then maybe I'll ask one final one. So another question in the chat window: if you had to give a single piece of advice to medical students in order to prepare them better for the future of healthcare, what would you say?
Be compassionate. I don't think, if you're worried about a machine replacing you, then you're a pretty robotic person. Because the thing that you get out of interacting with a clinician is the human connection, an individual who cares about your health, who is well informed, who's going to help you, right? Like if you really think that a robot could replace your doctor, I feel that's not a good doctor.
Great. So I know you have to run in just a minute, so I do want to ask one final question, which is sort of maybe my own sort of personal advocacy for the goal of explainability or interpretability, which is not so much about whether it's important for clinicians to understand the basis of the advice that they're being given by an AI, but that at some point, explainability is important for doing the basic science that would then sort of uncover what to do next.
Yes.
And so I wonder if you can comment on that briefly.
I am very strongly in support of using maybe explainability methods during co-development of novel scientific work, right? So I've seen this work really well, for example, with drug discovery, where you're trying to probe, like, well, where are you looking? Why did you think that? Oh, well, that's obviously wrong. Like, do this instead. But that's because those development and iteration cycles are very fast. It's often a tight collaboration between a subject matter expert and a technical person. And it's not deployed. It's during development. There is no end user. Like, the scientific team is the end user.
Well, I think that's all the time that we have. I want to express both my gratitude to you for coming and speaking today. I also am appreciative for the Data Science Institute and the Data for Good seminar series for hosting this event. And thanks everyone who has been able to attend. And we'll go ahead and close there.
Thank you so much.
Thank you very much.
Thank you all.